Now, this picture works fine as long as you have a constant force. If you, along a straight line path, if you have a constant force along a path that isn't a straight line, or even a non-constant force, but for now I'll just talk about a constant force, force of gravity straight down, along a curved path, how do you do this? Is it valid to just do your force dotted with a vector from your initial to your final point? Of course, I haven't indicated the direction along this curve, but this is the direction in which I drew it, so let's specify that. In this case, for the gravitational force, it is, because the gravitational force is what we call a conservative force. But let's not worry about the details of that. Let's just see how we would do a line integral for this, or what the line integral would mean for this. The line integral basically means you just do what you normally do with any integral, is you have an interval from some start to some finish, and you partition that interval. So we could partition this curve into small intervals. Now, the curve is generally going to be parameterized, and you actually partition the parameterization, but that's effectively the same as we just partition this curve into a bunch of little segments, and on each segment we calculate the displacement from the beginning to the end of that segment and dot that with the gravitational force. So here's a typical segment. Now, I've kind of enlarged that down here. Here's your segment. It goes from here to here, and here's your delta S sub I. And as you would know from doing Riemann sums and so forth, we usually use I for the ith, for whatever happens within the ith interval of the partition. So this is the ith interval of a partition of, we would usually say, n segments. And your delta SI is just the vector that starts here and ends here. Starts on the curve at the beginning of the partition and ends on the curve at the end of the partition. Now, we take that delta SI and we dot it with our gravitational force. So we get F dot delta SI. And we sum that up. Now the sum, we could say, okay, sum goes from I equals 1 to n, if we want to, but it's pretty clear if we just write the summation sign that that's what we mean. We kind of regard that as implicit. And we say that the potential energy is the sum of all the contributions from all of the subintervals of the partition. Then we shrink the intervals of the partition in one way or another so that the lengths of all the intervals approach 0, and that leads us to, in the limit, to an integral. So I've got an arrow indicating the integral. Now we would say the limit of the sum from I equal 1 to n of F dot delta SI equals the integral. Okay? Now, change of potential energy, of course, is equal to the negative of that sum. So the change of potential energy will be equal to the negative of this integral. Now, how you actually set up that integral and perform it, it's not something you're going to have to worry about in this course. But if you're in the engineering curriculum, you're going to have to worry about it in your vector calculus course, and I'll leave it to that course. This course doesn't have a vector calculus prerequisite, so we're not going to actually construct any line integrals, but I'll still refer to the process. Okay, I'll refer to the idea that we just sum up the contributions of work from a bunch of tiny intervals, take a limit, we're going to get an integral, and that's going to be the work done by the force. And your textbook refers to line integrals without asking you to actually calculate any line integrals. Now, the rigorous statement of what it means for force to be conservative, if we let A be the initial point on this curve and B the final point, then this integral would be an integral, we would say, from A to B along this path. Now, in general, when you do an integral, if you change the path, you kind of expect the integral to change. However, For a gravitational force, that's not going to be the case. Really, you're just summing up the product of the gravitational force with the vertical change on each small interval. If you add that up, sometimes the vertical change will be positive, sometimes it'll be negative. The total vertical change here is just the vertical change from A to B. So if we just did the vertical change from A to B, dotted with the gravitational force, that's going to have to be equal to the line integral of the gravitational force, because the gravitational force is always constant. Okay, I'm not going to prove that, but that's fairly straightforward to understand that. To say that a force is conservative, there are many different ways you can state this. One is that it's a gradient of some scalar function, but you don't know what that means. Another that you get some sense of from this discussion is that if we integrate the gravitational force dotted with the delta S from the point A to the point B, then we could integrate over the path that I've indicated here. We could integrate over a straight line path from A to B. We could integrate over a straight line horizontally from here to here, and then vertically from here to here. There are many different paths, infinitely many different possible paths from A to B. And the fact that gravity is conservative, the definition in your book is that a conservative force is path independent. That means that the line integral from A to B of F of gravitational force dot ds is the same for any path from A to B. It doesn't matter what path you take. Now, for a constant gravitational force, again, since we're only talking about the effect of vertical changes and they kind of add up the same no matter how you go from A to B, the positives and the negatives add up to just that much of a positive change in position in the vertical direction. It's not hard to kind of understand how that works for gravitational force, but that's true for a number of different types of forces. It's true for gravitational force when you move away from a planet where the gravitational force isn't constant. You move within the gravitational field of a planet, this still holds. And that can be proved, but it's proven by the methods of vector calculus or multivariable calculus. And again, it's beyond the scope of this course. But this is a more rigorous idea, a more rigorous explanation of what it means for force to be conservative, and it's done in terms of line integrals.